Welcome to 2-4. Today we're going to talk about continuity. Now, informally, a function is continuous if you can draw the graph without picking your pencil up off the paper. Now, obviously, that's not a great math definition, so the way we define continuity mathematically is three things have to hold. One, a is in the domain of f. That means f of a is defined. Two, the limit as x goes to a of f of x exists. And three, 1 and 2 are equal. The limit as x goes to a of f is f of a. Now actually, 3 implies 1 and 2, so we really only need statement 3, but when we're learning about continuity, it's helpful to break it down into exactly 3 statements. Now here I've got the mathematical definition of continuity just for fun for you, and don't worry, in a few years you'll be able to read that without any problem. So let's look at some examples. Which of the 3 rules of continuity is first violated at x equal 2? All right, so statement 1, we need f of 2 to be defined. So f of 2 is -4. That exists, no problem there. 2, we need the limit as x goes to 2 of f to exist. Well, that limit is -3 from the picture, so that's fine. It's statement 3 where we have a problem. The limit as x goes to 2 of f is not equal to f of 2 because one value is -4, the other's 3. So here's where we have our problem. Okay, this is a limit we saw last time. I graphed f of x equals sine x over x on Desmos, and the graph looks continuous everywhere, but it's actually not. So the first rule that's violated is rule 1. F of 0 isn't even defined. F of 0 does not exist. However, the limit does exist, and the limit is 1. Okay, if a function's not continuous at a point, we say it has a discontinuity. Discontinuities come in 2 types, removable or not removable. Removable means exactly that. We could redefine the function. If I moved that point down there, I could make that function continuous. Non-removables come in 2 other types. Jump, there's no way I can make this function continuous. And infinite, meaning there's a vertical asymptote. There's no way I could make that function continuous. Most of the functions we work with will be continuous on their domains. And so polynomials, rational functions, exponentials, and logs, they're all continuous on their domains. And we can combine continuous functions to get more continuous functions. For example, if I add 2 continuous functions, I get a continuous function. So let's look at these 3 examples and determine where they're continuous. So really, we just need to find their domains. So the first one, let's factor the denominator as x minus 1, x plus 3. The domain is the set of all x where the denominator is not 0. So we need x not equal to 1 or -3. And so the function is continuous everywhere where x is not equal to 1 or -3. And we'll see in a minute that that function has a hole at 1 and an asymptote at -3. F of x equals e to the 3x. Well, the domain here is all x. So that function is continuous for all x. There's no value I could put in for x that would make e to the 3x undefined. Absolutely nothing. Remember what the graph of e to the x looks like. Looks like that. E to the 3x is very similar. All right, and logarithm, we know that to find the domain of a logarithm, we take the argument out and we set it strictly greater than 0. So that would be x greater than 1/2. That's the domain, and that is also the interval on which f of x is continuous. So continuous on this interval. Okay, let's talk about removing removable discontinuities. So this is the function we looked at above. Can we define f of 1 so that f is continuous at 1? And we see over here in the picture, there seems to be a hole when x is 1. So let's find the limit as x goes to 1 of f of x. Now, that's equal to the limit as x goes to 1, I can cancel those x minus 1s as long as I keep writing the limit sign. If I drop the limit, that wouldn't be correct. All right, well, that's just 1/4. I can take the limit. So I took the limit here, so I dropped the limit sign. So we would want to define f of 1 to be 1/4 to make that function continuous and to fill in that hole. And a way we can do that is we could make a piecewise defined function that will agree with f everywhere, except it will fill in the hole. So let's let g of x equal 1 over x plus 3 if x is not equal to 1, and 1/4 if x is equal to 1. All right, let's talk about piecewise defined functions and making those continuous. So here I've got a piecewise defined function, and I want to know for what values of a, f will be continuous at x equal 3. All right, so I need to find the left-hand limit and the right-hand limit and make sure they're equal. The left-hand limit is equal to the limit as x approaches 3 from the left of f. Now, if I'm coming at 3 from the left, I need to use the upper formula because that's the formula I'm going to use if x is less than 3. And if I come from the right, I'm going to use the 2ax formula. So this is x squared minus 1. Now, whether I'm coming at 3 from the left or the right, I can just use substitution to find this limit and put 3 in. 3 squared is 9. 9 minus 1 is 8 because nothing bad happens. In the right-hand limit, I'm going to do the same thing except use the other formula. Limit as x goes to 3 with a plus sign over it of 2ax. Take that limit, put 3 in for x. 3 times 2 is 6. 6a. So what I need is for those two limits to agree. I need 8 to be equal to 6a. So remember, the goal is to solve for a. So this implies single double arrow, not an arrow like that. That's not right. You want double arrow, meaning implies that a is equal to 4/3. Okay, we'll do one more. So same problem, except now I've got the variable over here on the interval. We want to find c so that f is continuous at x equals c. So again, left-hand limit. You should probably pause the video, do this one yourself, and see if you did it right. So left-hand limit, limit as x approaches c from the left of x squared minus 9. I'm using the upper formula for the left-hand limit, and I can use substitution to find that limit. That's c squared minus 9. The right-hand limit is the limit as x goes to c plus sign of 6x minus 18. Just use substitution. That's 6c minus 18. Okay, and now we need the left-hand limit to be equal to the right-hand limit. C squared minus 9 is 6c minus 18. Okay, this is a quadratic, so we want to move all terms to one side and see if we can factor. C squared minus 6c plus 9 is 0. And sure enough, that factors as c minus 3 quantity squared equals 0. So c is 3. Okay, I want to finish up with an important theorem. You're not going to use this theorem directly, but we use this theorem to prove a lot of things in mathematics. And you will use it as you get to more advanced classes. So suppose f is continuous on a closed interval. The two big requirements here are continuous and a closed interval. If m is any value between f of a and f of b, then f of c is m for some number c between a and b. So what does that mean? I think it'll make perfect sense when you see a picture. M is any value over here between f of a and f of b. And the theorem says that if f is continuous and the interval is closed, then there's got to be a c down here between a and b such that f takes on the value m at c. And you can see why the requirement of continuous is important. If there were a hole there, then that wouldn't happen. But there can't be a hole because f is continuous. A corollary is an important result we get directly from another theorem, is that if you have a polynomial, polynomials are continuous everywhere, and p of a and p of b have different signs. So in my example, p of a is up here, it's positive, so a is 0, and p of a is positive, b is 1, and p of b is negative. If those have different signs, then the graph has to cross the x-axis to get from one value to the other. If it's going to go from positive to negative or negative to positive, and it's continuous, it's got to cross the x-axis somewhere. That's what we call a root. So you've got a root somewhere between 0 and 1. All right, and that is the end of this section.